problem with the migration matrix. I've got the migration matrix set up. Well, you could leave the migration matrix as it is, but you have to flip the 200,000 and the 100,000, okay? Because what you're going to do is you're going to multiply this first row times the column of the matrix. So you're going to do 0.7 times 200,000 plus 0.2 times 100,000. That's how I got the 160,000. But when you go back and reread the question, 70% is supposed to be 30% of Mexicans leaving Mexico for the US yearly, so 70% behind, right? So we should be taking 70% of the Mexican population, right, to determine what the next Mexican population is going to be in the next year. But 200,000 is the US population, right? So I have it set up a little bit wrong. So we should, probably the easiest thing to do is to change the migration matrix. So it should be, so 0.7 and 0.2 need to be switched so that you're multiplying by the right numbers, and the 0.8 and the 0.3. No? Still wrong? No, you don't have to, because now you'd be taking 20% of 200,000 and 70% of 100,000, which I believe is correct. Okay. Yep. So yeah, we also have to flip 100,000 and 200,000. All right, hold on, let me think it through. Okay, so if I keep this 200 and 100. All right, so the 200,000 is the US population, right? So what do I want to take for the US population? I need, the US keeps 80% of its own population, right? So I'm going to put a 0.8 here so that I'm going to do 80% of 200,000. And then so the US keeps 80%. How much does it take from Mexico? 30%. So I'm going to put a 0.3 here. So you have 80% of the US population, 30% of Mexico's population, add them together, that makes the new US population. All right, and then for Mexico, 70% stay behind, and so 70% of the Mexican population, and then 20% of the US population. So that would be your migration matrix. Multiply it by the US Mexico population 3 times, and you'll get the population in 2003. All right, let's see if I can do one of these without making a mistake. All right, so I have, this is a traffic flow. It could be literal traffic like on streets. It could be traffic in a network of like some kind of computer system. So we want to solve for the unknown traffic flows here. I've got them labeled X1, X2, X3, and X4, and X5. So if I want to solve for them, the key is that the flow in to each intersection or node has to be equal to the flow out. So let's look at each intersection, right? So at A, everything that flows in has to equal everything that flows out. So flowing into A, I've got X2 and X5. That's in. And then flowing out of intersection A is a 300 and a 700. At intersection B, my flow in is a 500 and an X1. And my flow out is X2 and X4. Intersection C, coming in is X3 and X4. And flowing out is 200 and 400. So, I mean, if you want to, sometimes it's helpful to think of units. You can think of these as cars, right? Coming into the intersection and leaving the intersection. So the number of cars that enter the intersection have to also leave. They can't just come to the intersection and like poof, disappear, right? So the number in has to equal the number out. And then finally, intersection D, we've got flowing in 200 and 500 cars. And that has to equal the number of cars that flow out, which would be X3 plus X5. And then there's also one more equation that is missing from your solution set here. There's one more equation that says the total flow into the whole system has to equal the total flow out of the whole system. So if this is like a city, right, the number of cars that come in has to equal the number of cars that go out. So we've got one more that says, I wrote it down, but it must not have been on this sheet. That's okay, we can recreate it. So everything that's flowing in would be 500, X1, another 500, and a 200. 500, 500, 200, and X1. So it's everything that flows in. That has to equal everything that flows out. So flowing out, I've got a 700, a 300, a 400, and a 200. 7, 3, 4, and 2. Did I remember that correctly? 7, 4, 3, and 2 are flowing out. So now you have 5 equations with 5 unknowns, x1 to x5, and you can set up a system, row reduce, and solve it. And I'll let you play with that on your own. The solution's written out here. The solution comes out correctly even without the last equation, and it was left out of this solution, but it comes out the same. All right, last application is balancing chemical equations. So if you've taken chemistry, you're gonna be like, oh, why didn't I know how to do this when I took chemistry? Okay, so it's just really makes a big time saver when you're balancing chemical equations. So I've got a chemical equation here. I'm going to set up a vector equation. Each vector is going to be the number of molecules I have of each of these things. I'm going to have H, O, N, K, Al, and S. Okay, so each vector is going to be the same order. Okay, the number of atoms of each of those things that I have. So I have to have some weights in here. So I'm looking for the number of molecules to make this thing balance, right? All right, so these are what I want to know: x1, x2, x3, x4, x5, x6. All right, so I take my x1, and it's going to get multiplied by the number of atoms of each of these things that I have. So in this first molecule, NH4OH, how many H's do I have? 5. So I put a 5 there in the H spot. How many O's do I have? 1. How many N's? 1. K's? 0. Aluminums? That is aluminum, right? Making a fool of myself. Okay, good. S, 0. All right. And then X2, I do this for each molecule. What weight do I put on the next molecule? So I have to count up how many H's I have. I've got 24 because I have 12 H2Os. And then for O's, I have 8. I've got 2 O4s, which is 8, and then 12 in my H2Os, 20, right? 20. And then for N's, I don't see any N's. K's, I have 1. ALs, I have 1. And S's, I have how many? 2. Okay, so that has to equal the other side of the equation, and we just keep setting it up like this. I'll just finish writing it out for us. X3 gets multiplied by 3, 3, 0, 0, 1, 0, plus X4 times 8, 4, 2, 0, 0, 1, plus X5 times 1, 1, 0, 1, 0, 0, plus X6 times the last molecule, 2, 1, 0, 0, 0, 0. All right, so I have a vector equation. Vector equations can be translated to an augmented matrix. So it would take a little bit of work here. You could translate this to a system of equations that says 5x1 plus 24x2 equals 3x3 plus 8x4 plus x5 plus 2x6. Get all your variables on one side of the equal sign. So there's a little bit of translating to do here. I'm just going to jump to the row reduced matrix. And you can maybe on your own at some point make sure you know how to make this translation. Probably on your quiz, you're going to have to be able to make a translation like this. All right, so I've got 5, 1, 1, 0, 0, 0, 24, 20, 0, 1, 1, 2, -3, -3, 0, 0, -1, 0. So these first two were the same as these columns because I was moving everything from the right over to the left. And so the rest of the columns are going to be the negative of what's in there. All right, so then I have -8, -4, -2, 0, 0, -1, -1, -1, 0, -1, 0, 0, -2, -1, 0, 0, 0, 0. And then the other side of the equation is going to be all zeros once you move everything over. RREF. And this one I'm going to finish solving just to show you how you end up with what the x1 through x6 is. Because your general solution is infinite. There are lots of x1s through x6s that can balance this equation. So we end up with x1 is 1/3 x6. x2 is 1/12 x6. x3 is 1/12 of x6. x4 is 1/6 of x6. x5 is 1/12 of x6, and x6 is the only free variable. So it's the free variable because that would be the only column when you RREF with no pivot. So then to decide, like there are infinite solutions here, so to decide you just choose your free variable x6 as small as possible so that all of your weights will come out to whole numbers. So what should I take x6 to be? 12. So if x6 is 12, then x5 would be 1, x4 would be 2, x3 would be 1, x2 would be 1, and x1 would be 4. Those are your weights that balance the chemical equation. Yes. Yes. So in order to have, in order to make an augmented matrix, you have to have all your variables on one side of the equation and then just the constants on the other side. So I was going from this vector equation. And so just think about the first equation that this says. This says 5x1 plus 24x2 equals 3x3 plus 8x4 plus 1x5 plus 2x6. So I took everything on the right side of the equation and subtracted it, moved it to the left side of the equation so that it said 5x1 plus 24x2 minus 3x3 minus 8x4 minus x5 minus 2x6 equals 0. And so then this all ends up, these all end up negative because I subtracted them to the other side. All right, so that's the 4 kinds of application problems. The application problems are not on your quiz today. They'll be on the next quiz. And that's all I wanted to make sure we got through. I'm going to hand out the group quiz. And if you remembered, you're allowed to bring a note card for quizzes, so you can have that out. If you want, you can like jot a couple things down on a little slip of paper while you're working on the group quiz and use it on the individual quiz.